Okay, so earlier I had asked the topics you'd like to hear, and one of the topics that you guys recommended was AI in healthcare. So that is what we are going to do today. I could have thought of inviting many people from outside, but I decided to um, just present it in present the work that is happening here at the AI Institute, because at least among my contact and network, this is where the among the largest amount of work that is ongoing on the healthcare. So what do we in this fourth floor in this on the fifth floor here? What are the things that we work on in the AI Institute? So in the center, you see a bunch of AI topics in AI that we work on. There are a number of them. You can see the core is neo-symbolic or hybrid AI, enhancing basically the language models with and multimodal models with knowledge. You can see also we have extensive work going on generative AI and LLMs. So our work on generative AI and LLMs is more about dealing with the problems that generative AI problem has, statistical AI problem has. So you have hallucination, fake news, deception, toxicity, deepfakes, misinformation. So we work on those topics. On the positive side, meaning for the future AI models, we work on the so-called neo-symbolic or hybrid AI. And then, for many applications, people need more reliable, trustworthy AI. And for that, we have this interpretability, explainability, safety, trust, and ethics in AI. Natural language processing, collaborative systems, deep reinforcement learning, vision. These are all major topics that we work on. Now, what we also do, in addition to this foundational research, is that we also work on a broad variety of applications. And given your interest in AI, in particular, we work on clinical AI issues. So right there at the top, you see medicine, healthcare, and nursing. And within that, we work on nutrition, neurodevelopment disease, asthma, diabetes, hypertension, autism, cognitive disorder, oncology, many of this kind of stuff. Very large disease. In fact, we work on a majority of issues that majority of top 9 or 10 diseases that are there in the US or in the world, in fact. And we also work on public health, particularly mental health, addiction, epidemics, and epidemiology, right? People who study the progression of disease. So as you can see, there's a very and we work on pharma related topics, also this neuroscience, brain science, and cognitive science. So they are all sort of related to healthcare and allied fields, right? Very extensive. I can literally present for the entire day or more if we cover all of them. So we're going to take some samples with the idea of sharing with you interesting AI or computer science problems. And then Kaushik will go deep into one of them with then one technology relevant to healthcare. And then we are going to show you 2 concrete applications that we work on among many. So these are my PhD students, a couple of masters and 14 or 16 PhD students. And many of them are involved in health. The reason I'm showing you is not because I want to show all these faces, but that, for example, Utkarshni worked on asthma. And Revati worked on asthma and also on nutrition. Usha worked on the cognitive decline and also on public health addiction issue. Kaushik is going to talk about what he works on. Vedant worked on COVID and basically public health context. Deepa works on brain, science, meaning MRI images and looking for lesion in the images and basically aphasia, right? Loss of language functions. Mega works on mental health. Naeem works on the same sort of things as Deepa. And so these are some of the people. Manas also did extensive work on mental health, right? So these are some of the topics that we've been working on. Again, as I said, this is not the entire list, but we thought there are some interesting computer science and AI aspects with respect to this diverse health application. So we said, let's talk a little bit about this. And this is just to give you a sense of the topics involved. So one topic is what is called as public discovery. In that there's vast amount of medical literature. Every year there is more than 3.5 million new scientific publications, right? And so there's a lot of knowledge, because many of the publications that go on PubMed, they involve clinical trials, right? And or clinical trials, animal trials, and there's a lot of information that we have learned, right? So you can learn very interesting thing from all of those items. And it so happened that some scientists have gone through large amount of medical literature and found things that we did not know earlier on, right? So for example, this discovery of dietary fish oil disturbs platelet aggregation that causes Raynaud syndrome, right? That kind of discovery was done not by running experiments or human observations or clinical trial, but by going through literature and finding a part of these from some literature and other part from other literature. And so you can see there are a lot of concepts involved here, right? Obviously, many of you may not be aware of what is prostaglandins or all those kind of stuff, but nevertheless, these are all biology, medical concepts essentially, and how they, are related to each other. One converts into another, one simulates, one disrupts, is a type of something. All this knowledge was extracted from scientific literature. So, in one way of looking at it, this is a one of the extreme or significant example of natural language processing and natural language understanding, right? And that's a natural language understanding and natural processing is a very large field of AI, right? A very large field of computer science as a whole also. Yeah, you're dealing with text and learning from the text. So, in fact, one of my PhD students' dissertation was very much in this particular topic. He built tools and techniques and technologies for processing of these highly specialized medical and other texts that converted into new findings. And if earlier humans had done this, analysis of text and found such things, discovered these items, what if machine can go through? Because machine can go through this text much faster. So if we can have machines identify this kind of relationship that I've shown you, we can substantially scale discovery of knowledge from existing literature. Here is the second problem, a very different example in this particular case. Of course, in healthcare and with AI. So in this case, we worked on the issue of asthma in children. What is causing asthma in children? And it is a highly personalized disease, right? It's a chronic disease and highly personalized. Somebody is affected by pollution. Somebody is affected by a dryness in air, or in the winter, close air, there is a dry air, for example. Somebody is affected by pollen, right? somebody is affected by some other things. So there are many causes, many allergies and other causes for creating the symptoms that then lead to asthma attacks, or that describe asthma attack, right? So in this particular case, we built a system, which is a mobile app running on an Android platform, and we had a bunch of um, sensors or devices, consumer grade Fitbit that will tell you sleep, for example, and activity level, and then peak flow meter or some other way to measure the lung function capacity. Like when you have asthma, you have wheezing, and then you have less capacity, the lung shows less capacity. And then you also got from the web services a pollen count, what kind of pollen it is, weather, air quality, and all those kind of stuff. And we would collect 1800 and up to 1800 and some data points per patient per day. Right? So it's a big data, health big data at a personalized level. And we analyze the data. So you see a dashboard there, and there you can make correlations. You see symptoms, and you see the values that we have collected, right? So they allow you to, and then on this you can do causality study. So causal AI and causality is a part of an important part of AI research and computer science research. And one of the students, Utkarshni, her dissertation is going to be causal AI. Okay, so there are, there is a formal research work done, large scale data representation of causality, development of algorithm, that will then identify causality. So there is this another very exciting area of work in healthcare, but this is personalized healthcare. Within the area of personalized healthcare, we developed a strategy called augmented personalized health, and that was being able to monitor, like you're monitoring using Fitbit, being able to look for analyze this data and find what is affecting you, to see how the disease progresses over the period of time, and many such things. So there is a holistic view of how a human health can be managed at a personalized level using this kind of technology and research. Here is a another one. There is a large, we work with psychologists and people who work on aphasia and autism and other diseases like that. And here, one of the project is on using AI for understanding cognitive decline from speech or other other items. So for example, here you see this is a test. It's called this is a cat on the tree and cookie theft. So the patients are shown these pictures and they are asked to describe, and you do the recording of what they speak, and somebody who has still good cognitive skill would be presenting the ideas very coherently, would be not stammering as such, or the speech would be fluid, and there are many other aspects, right? So you capture them, they will describe all the relevant concepts. Somebody who's cognitive, who has significant cognitive decline may not be able to coherently describe those concepts, right? So there are many parts of the data that you collect, many data you collect, demographic, and then language analysis at the semantic level, like you see percent of noun verb index, main concept analysis. These are a variety of NLP techniques: lexical, type token ratio, propositional density, content density, fluency, sentiment, vocal parameters, acoustic and others. You do all that kind of analysis. And then, for example, just the main concept analysis that is mentioned here, that involves all of that, analysis. So a fairly number of concepts involved in NLP, natural language processing, but very different kind, right? So speech processing, audio processing, just like vision, computer vision is an important area. Speech and audio is also another important area. And so those are also being done here. But when you do all of these things, then you are able to create a score. Now, the whole positioning of this was that we, all this work would involve that a patient comes to a lab, clinical place, administered these tests, recordings are done, they go to a human who is specialized in doing all this kind of analysis by hand, by looking at the text, by listening and all that stuff. And then they will fill out a form, giving some rankings or marks, and they add that up, and based on that, they will say how much cognitive decline there is. So here, and that will take several hours. Here, a machine can do it in a matter of seconds, right? And then, of course, in any science, we have to prove that what you're getting using a technology is at least as good as what a human can do, right? And it's very interesting that a human can get tired, may lose attention and all that. Machine does not do that. So it is possible sometimes for machine to do better than human, right? Plus the number of, yes. Yeah. Well, not just the transcript, but also speech itself. Speech is also processed. Here, we use AI in the context of aphasia. So aphasia is when somebody has a stroke, parts of the brain gets dead, becomes dead, because like stroke leads to blood coming out of your veins, arteries and veins in the brain, and they clot, and that leads to tissues becoming dead, and that where the tissues are dead, that part of the brain function gets affected. One of the brain functions that frequently gets affected is language function, and that is called medically or clinically aphasia, right? So here you have MRI image that is being processed. There are billions of dollars spent in mapping the brain and creating brain atlas. So those brain atlas, they have determined what are the anatomical part of the brain, what are their functions, many things of that nature. And then you do analysis of the brain, and you identify lesions from that. So there are a whole bunch of techniques that are applied in finding that, and then from that you predict how basically so instead of a human looking at brain imaging, here computer vision algorithms are identifying those kind of things where each part of the brain is affected, what is the function of brain, what does that predict in terms of language functions. And that is the kind of work in this particular case, right? So this is a computer vision part of the AI that gets applied here. Okay, so with that, and there are many more, but that will take away our whole time. So I'm going to turn over to Kaushik. Kaushik is a PhD student, a senior PhD student. But Kaushik, you have how many papers now?
I don't know, greater than 20 years.
Yeah, so he's probably 25, 30 papers already. He already has 900 citation to his work. So if you go to the computer science department and look at faculty, significant majority would not have that many citations. So anyway, that's pretty significant, and it's routine. Earlier I mentioned Manas, he had 1,000 citations by the time he graduated. Very big achievement. Anyway, so he's going to take one a core aspect of AI that we worked on with the healthcare application, and then we'll step back. Okay. And by the way, he was invited and paid to visit a medical center in Florida to give this talk.
Thank you, Dr. Shet, for the introduction. So what I'll start with is introducing the core technology behind a healthcare application that is meant for uh, um, mental health management for an individual. Um, and I'll build up to the aspects necessary to implement that kind of technology, one slide at a time. So what I'll start with here is what is the concept of semantics? So semantics generally means that you want to associate meaning with otherwise data artifacts that don't inherently have any meaning. For example, in a self-driving car scenario, you have a bunch of sensors on the vehicle. For example, radars and depth sensors and all kinds of things. And they record numbers that are supposed to mean something in being able to inform the control system for the car, how to steer or act in a particular environment. But when you just record the numbers as they don't automatically mean something. You have to assign semantics as necessary for your downstream application. Uh, in a system, in a cyber physical system such as this, things are slightly maybe more palatable. For example, when you see a number corresponding to the position of a car, you have some sense of meaning. And you also can guess how that can inform your steering controls. On the other hand, in the type of applications that I work on in mental health, the input is natural language. And now when a computer program sees natural language, it sees a bunch of strings. So it is completely non-trivial. How do you assign semantics to a bunch of strings? Dr. Shad showed some examples, how you can use a knowledge graph or I'm not sure we use the term knowledge graph, but the first slide where he showed the discovery between the Raynaud syndrome and certain chemicals, that's what a knowledge graph is. It shows you how should you interpret strings depending on the downstream task that you're doing through conceptual modeling. Uh, so uh, these are, for example, knowledge graphs that are built for various kinds of downstream tasks. Um, it's not very visible, but I'll go through them one by one. The first knowledge graph in the tile A, that is related to how should you conceptualize disasters. So in a disaster scenario, you have various things such as what is the impact, what is the volunteer support available, what are the services in case of emergencies, and so on. So that's what you're interested in modeling out of all the data that you have. Similarly, in various different kinds of downstream applications, a lot of engineering effort goes into figuring out the domain model so that you can meaningfully assign semantics to the data that you have. More recently, maybe in the last decade or so, people have, instead of modeling it this way using human expertise and extensive effort towards knowledge engineering domain modeling, tried to pass data directly in its raw form to neural networks. And when they've then built techniques to visualize what happened inside this neural network, they've seen these kinds of pictures. This is the internal semantic space of a neural network. It creates meaning, assigns meaning to strings as a bunch of associations in an abstract vector space. Now, compared to the domain models that we saw earlier, maybe you would agree that this is a significant compromise. But the advantage here is that it's much more automatable and it can be applied to a larger scale. Or I should caution that for a particular type of task, these kinds of semantics can be pretty useful to start with. Eventually, for dealing with applications like healthcare, you'll have to get to richer domain representations, such as knowledge graphs. So, okay. So far, I talked about what is semantics and how do you assign semantics to raw data. But in an AI system, a typical AI system, you have, roughly speaking, three components. One is the semantic interpreter. Then the second one is, once you have a semantic interpretation, how do you reason over that? So in the way that AI has progressed over the decades, the earliest was called rule-based systems, so expert systems. Basically, in that era, the semantic interpretation was hand-coded by humans. They looked at the raw data and they decided that they want to model the data in a very specific way using a conceptual model. And then the reasoner was also pretty much handcrafted. So if you see concepts X, Y, and Z, then you should take action A, for example. They used to hand write those rules, and those systems were called expert systems. They were entirely rule-based systems. This was the first decade. In the second decade of AI, as big data became available, we moved to statistical learners. So with neural networks are one type of statistical learning machine. What we were able to do in this era is take the raw data along with minimal demonstrations. So for example, supervision signals regarding what are broad categories that the data is supposed to represent. To give you an example, if you get raw data about from sensors in an autonomous driving scenario, you at least have a few labels to work with, like, some numbers correspond to positions, some numbers correspond to pedestrian positions, and so on. So you have that minimal target demonstration supervision. The rest are raw numbers. Now it's up to the statistical pattern recognition machine to map those raw information into an abstract vector space. The main problem with this is I showed earlier how you can maybe visualize that abstract vector space by looking at which words are generally represented in this space here. But this is only an approximation. Truthfully, nobody knows exactly what is going on inside the internal mechanics of a neural network when it's constructing this vector space. Consequently, the reasoner that relies on these type of abstract vector spaces does produce an output relevant to the downstream task, but it is very difficult to judge the quality of the output for accuracy, explainability, all these factors which are very necessary for deploying AI systems in critical domains like healthcare. So neural networks alone, while they have seen a long list of successes in syntactic processing tasks, like what is the part of speech going on in text and so on, they're not readily in their current form applicable to critical applications like healthcare. So that brings me to our core body of work, which is called knowledge-infused neurosymbolic AI. That's a mouthful, so I'll go through it one token at a time. So knowledge here refers to the concept model that you saw earlier, the knowledge graph. It's illustrated here in that form. It's a bunch of entities and how those entities are related to each other. And the neurosymbolic part is there are advantages to neural networks. I mentioned some of them, that they can scale, they are very automatic, and so on. There are similar advantages to symbolic AI because it is entirely rule-based. You have interpretability, you know that the reasoning is exact, and so on. What we are aiming to do is combine the best of both those worlds, but use knowledge to do that in a downstream task relevant manner. For the reason for using knowledge will become clear as I show the demo. The neurosymbolic AI part will also become clear as I show the demo in the actual healthcare application. The second part of our research is called process knowledge infused neurosymbolic AI. So what this means is, if you imagine a search engine, and let's for now imagine that the technique that powers the search engine is knowledge infused neurosymbolic AI. What we also want to add on top of that is some guardrails. So if people search for harmful content, let's say, or toxic content, we want this search engine to say, I cannot answer this question, right? So this is a very basic example of a process. You trigger the search engine if it is within the scope of your search engine, otherwise don't do it, right? So that's a type of process. Okay, so all this is a very conceptual picture of knowledge-infused learning and process knowledge-infused learning and AI. And now I'll show a demo where these techniques are implemented in the context of individualized mental health management. Okay.
Hey, I'll be presenting a demonstration of that.
Sorry.
I think cut down the speaker mic here.
Cut down the. Audio.
Yeah. Try speaking now.
Yes. No, I think I'll have to screen share the audio, right?
Yeah.
How do you do that?
No, the audio from yours would anyways be recorded in this for them, so you don't need to screen share the audio.
Okay.
Once you're playing it, you speak in the microphone.
Hello. Today.
So here's what I'll do. I'll play the video and I'll narrate over it so that everybody can hear. So in this system, what is going on is in this flow diagram, you see that there is a patient and then available to the system is also provider notes. So this patient already has a care provider before the functioning of the system starts. So the system has provider notes. It has a conversation record of the conversation that has gone on so far. It has criteria for safety checks when it is making decision support suggestions. And it has a natural language generator. So whenever it processes what to say to the patient, there's a natural language generator which then verbalizes that to the patient. The most important part here is the medical guidelines. Whenever a behavioral health management system is deployed, when doctors suggest what is the best practice for a patient, they follow textbooks, they follow guidelines to the T. And so this system is expected to do the same, right? Okay, now, okay. So here, what you'll see is there's in the front end, two views to this chatbot. One is what the patient sees, and the other is what the care provider sees. So as the patient is engaging in conversation with the chatbot, in the backend, a graph of the interaction is created. So I'll pause here for a second. Yeah. So what does that graph tell the provider? So what that graph tells the provider is, in this particular example, that the patient is taking a drug called fluoxetine. That's an antidepressant. And they're also taking a drug called ziprasidone, and that has to do with blood pressure. And the counteracts edge, which is obtained from a knowledge source called UMLS, it's a Unified Medical Languaging System, shows that these two should not be taken together. That's what counteracts mean. Now, as this conversation carries on, what the chatbot finds is that the patient is having adverse reactions as a result of this bad combination. And the adverse reaction, specific kind of adverse reaction, is restlessness, right? That's what the conversation reveals as it goes on. And with this information, what the chatbot has the ability to then do is construct a hypothesis for the care provider. The chatbot, what it will not do is directly make suggestions to the patient, but it has the ability to construct a hypothesis which the provider can then offline act on, right? So this is an example of knowledge infused learning that I showed conceptually earlier, where you have a knowledge graph, you have natural language text, you use the knowledge graph to make semantic interpretations given the natural language text, and then make appropriate suggestions for this healthcare task, right? Now I'll skip over to the process knowledge part of it. Let's see. Yeah. So this chatbot is meant to only handle cases that have mild mental health afflictions. Nevertheless, it is equipped with identifying when the case is tending towards more severe cases. In this particular slide, we see an example of when the patient is displaying signs of suicidality. So there's very specific flowcharts that clinicians follow to determine if a patient is exhibiting a sign of suicidality. And the chatbot is also equipped to analyze the patient's responses against this flowchart and determine what kind of behavior they're showing. The behavior categories that you see here are they're indicating suicide, they're ideating on it, or in the worst case, they have actually attempted something, right? So this is an example of process knowledge infused learning. Okay. So this system has a lot going on behind the scenes, and I've linked here 2 playlists. They show in excruciating detail the individual components of what goes into building such a system, if you're interested, right? Okay. So here, that was mental health management for an individual. But what we've found more recently, this is in collaboration with the School Behavioral Health Academy here at the University of South Carolina, that there's a systemic issue. Even if a chatbot is able to suggest very good things to the provider on how to deal with a particular patient's case, there are regulatory bottlenecks sometimes, many times. And the problem is that the providers aren't very aware of the scope in which they can act. And these tiered support systems are called multi-tiered system of support, or in short, MTSS. The top tier decides that clinical intervention is required. The bottom tiers decide that a milder form of intervention is required, like enroll the patient in anger management, for example. And in each of those tiers, the regulatory framework within which the clinicians or support staff are supposed to operate is very detailed and often inaccessible to the actual care provider. So the AI system's role here is then to help out the care provider in figuring out the regulatory framework within which they're supposed to act. So I'll now play the demo, so you'll see this.
Diverse educational landscape.
So for the people online, we'll put a link in the chat so you can see this later. I apologize for not being able to share the audio right now. Yeah, so we'll put a link for you to be able to see this afterwards.
Kaushik, can you unmute, please?
Yeah. Oh, sorry. The question was here. Okay.
Yeah, how often you updating the model? So, you guys know that, a large language model could cost over $100 million and many months and 10,000 GPUs to train. While it has a lot of value, if you look at my last week or so, about 2 weeks ago, I gave a keynote in Barcelona. And we start out by discussing, the lot of challenges of generative AI, not just the cost, but the hallucination, meaning that you can't rely on the answers. They may be just simply made up, right? But beyond that, what you see them being used for effectively are for question answering. So better information. So this may be a future of the search that instead of getting search results from Google, you can get more combined integrated answers from multiple sources using generative AI. But what you notice, and they are used by for creative composition and image generation and all this kind of stuff. But they're not used for applications in the industry where you are essentially doing a task in a very reliable way, consistent way, explainable way. So that's why we have come up with this new, hopefully future generation of models. But the models are lightweight because they are only solving specific tasks. So ChatGPT, you can ask any question about anything. Here, the models solve the specific problems for which they are designed, helping personalized nutrition, mental health, across the school, behavioral mental health, things of that nature. There's a third one called smart manufacturing for the errors that occur on the assembly line and that kind of stuff. So they are not, aware of everything else in the world. They are aware of what they do. This means that in addition to the compact, custom, and symbolic, there's a fourth element, we call it on demand. So we are building a platform on which anybody, any company or any developer can come and train their model and take it. And the whole process would have significant automation. So you might have heard of machine learning pipeline software. So here we are basically having new pipeline where you have data-centric things, knowledge-centric things, human expertise, they're all brought together to create the model. But this pipeline, kind of automates the workflow, implements the workflow necessary to produce the model. And while it will vary, the production of this model will be few hours to a day or 2 or 3, much smaller. That means we can create a new model every week or every month, or when there's substantial change in the environment. And so we are moving towards a very different strategy on using future AI models. Anything else? All right, then. You guys know, have that web doc and the doc where where you can what is the schedule, so you can look up what is plan for the next doc.
Dr. Sheth, where should I paste the video for you?
Huh?
Where should I paste the video for you?
No, just you will link to your presentation, which has the videos. You in the chat, yeah.